So 22. First thing you have to do, think of it this way. You have variables on both sides of the equation. When you have variables on both sides of the equation, who do you pick up? Yeah. All right. So move the 2 cosine to the other side. You subtract it. So by subtracting it over, you might have the 2 cosine x is 1 divided by 2. And then you're asking, where is cosine? What angle has a cosine value that equals 1/2?
Wait, why isn't it equals 1? Oh, you just.
So which triangle has the adjacent of 1 and a hypotenuse of 2? So you have to be adjacent of 1, hypotenuse of 2, which means this has to be your 60. So, excuse me, where else is cosine positive? So it's positive in first, and it's positive in, correct. So that tells me that my answers are going to be pi over 3. And then if I move this down, it would be, take out a pi over 3 out of 6, there's going to be 5 pi over 3. You okay with that? You want to see 25 then?
Wait, I want to do 21.
We didn't have to. 21 it has a negative angle. We have to save a couple of things for you guys.
You didn't have to do 21?
No, it has a negative angle in there. And I'm probably going to throw at you guys one property because you kind of need to know a couple properties here. What do they have in common? Factor 1 out. Think of it as a GCF. Their GCF is cosine. And now you have 2 terms that you can set equal to 0. And you solve them independently. So you have a cosine of x is 0, and a sine of x minus 2 is 0. Add the 2, and it's asking you what angle has a sine value of 2. Well, that can't happen because sine is never greater than 1 or smaller than negative 1. So there is a no solution here. What's that? Yeah, absolutely. Because sine is only going to go between, remember, when you're dealing with the circle, the largest value of y is 1. The smallest value of y is negative 1. Everything goes between 0 or negative 1 and 1. And then cosine, what angle has a cosine of 0? Well, cosine is your x value, and x is 0 at pi over 2, 3 pi over 2. Okay. Yeah. Let's add difficult ones to this today. Yay. Now I want to go to, what do I want to do first? I want to talk about what's going to be called a general solution.
No.
Yeah.
No, I just dropped like all my papers.
Oh,
Wasn't about the general solution.
sounds like General South. General South, maybe. Thanks, Adam. So, yes, you guys are snacked. So, what I want to talk about today is something called general solution. There's going to be 2 different types of questions that we're going to ask when we're doing trig equations. One would be find the solutions within one ringy dingy, or within one revolution, or what's called find the general solution. So general solutions you're going to see is a little, it's kind of like an extra step to it. So we start with this. Let's see. Excuse me. What do you do first? Hmm? Add the 3. So we have 3 tangent cubed and a partridge in a pear tree. Then what? 5 by 3. Now what? Cube root. What's the cube root of 1? 1. Is it plus minus? No, because it's an odd number. So you go to the idea of what angle has a tangent value of 1? 45. Good. Now, we know that at 45 degrees, tangent's 1. We also know that that's pi over 4. Where else is tangent equal to 1? At 5 pi over 4. So when we're talking about what's called general solution, we want to see, is there something in common every time that I land at a pi over 4 with a like a coterminal angle? So if I start here, how long does it take me to get back to here?
Pi? Oh, 2 pi.
2 pi. It would take me 2 pi, every 2 pi, I would wind up back at pi over 4. Are we okay with that? Same idea here. If I start here, how long does it take me to get back to here? 2 pi. But with tangent, when you're at tangent, especially for the 45s, aren't these two angles, how far apart are those two? Pi. So no matter what, if I start at pi over 4, if I add pi to it, I get here. If I add pi to that, I get back to here. And back. And forth. And forth. And back. And so on and so on. So my general solution would just be how often you get back to the same spot. Pi times n, for the number of times you go around. So if I go around 7 times, if I do 7 pi, if I start at pi over 4 and I count 7 pi, 1 little 2 little 3 little pi's, 4 little 5 little 6 little pi's, 7, I'm still at one of the answers. That's what that means. Okay. That's what that means. Tangent's the goofball of them because sometimes you're just adding in pi. How often does it take you to get back to one of the answers? Okay, that's what we're doing. So tangent's the weird one. When we get into the sines and cosines, you could be off a little bit here and there, and we have to add in differently. So it's just that, again, we're just visualizing what does it look like, how often does it take you to get back to the same spot, and writing it out. Okay? General solution. Let's do a general solution of this nightmare-looking problem. Yes, those are cotangents, and yes, that's a 4th degree polynomial. Yeah. We would factor this like you would normally, but I'm going to show you guys a little trick to help make things look a little bit cleaner. We're going to use what's called U substitution. You ever heard of that before? When something looks really crummy, you let U do the dirty work. By doing this, and you're going to see us use this what we call U substitution quite often with this stuff, and there's something else later on that we do that again, but I forgot what it was. But it was some math thing. Now it just looks cleaner. Now it's just factored. Notice how your degrees go from 4, 2 to nothing? That means you factor it like you would any other trinomial. So what times what is negative 30 that you add together to get negative 1? Yeah, negative 6 and negative 5. I'm sorry, negative 6 and positive 5, excuse me. So 2u to the 4th minus 6u squared plus 5u squared minus 15. And I'm setting it up to factor via grouping. You all remember how much fun that was. So now you work with GCFs. When I work with GCFs, what do the first two terms have in common? 2u squared. And I'm left with a u squared minus 3. Next one I take out a 5. That'd be u squared minus 3. So far, so good? Two things in parentheses are the same thing. Yeah, write it down. And then we have, so far so good. Now that goes back now to the idea of setting up and solving for zeros. U equaled cotangent. So I'll just rewrite it now as cotangent squared x minus 3 equals 0. And 2 times the cotangent squared of x plus 5 is 0. One of those doesn't look like it's going to work out very well, does it? Cotangent squared, or 2 cotangent squared x plus 5 equals 0. If I solve that one, I'd have to subtract 5, divide by 2, and take a square root. I don't know about you, but do you want to do imaginary trig work? No, me either. So I'm not going to do this one. Because I can't. Right? I can't because you'll have negative roots. There is such a thing as negative or imaginary trigonometry on the complex plane. It is a thing. You'll see it next year. Just think about it. Imaginary sign. Imaginary sign. Isn't it great? I told you it's a thing. It's a real thing. Cotangent squared of x minus 3 is 0. What do you do? Add 3. Good. So if I add 3,
Good.
I'm trying to be supportive.
Isn't that more like motivational than supportive?
Yes! You can do it. So now what do? Square root. When you take a square root over an equal sign, what do you have to do? Now this is asking you, what angle has a cotangent value of plus or minus root 3? Cotangent is the inverse of what? Tangent. So cotangent is the inverse of tangent. So that means it would be,
That's 30, 60, 90.
it's a 30, 60, 90, and we draw it out. It's not, it's going to be adjacent over opposite, which means you're so your adjacent's the root 3, your opposite is the 1, and that's your 30, otherwise known as pi over 6. Now this being plus minus, that means that this angle is going to occur basically in all 4 quadrants. It's a matter of finding all 4. It's basically you're using that reference angle of pi over 6 to all 4 quadrants. So your pi over 6 in the second quadrant is, what is that, 5 pi over 6? Third quadrant is 7 pi over 6. And then the last quadrant is 11 pi over 6. We're okay with all 4 of those, correct? So now when we start talking about what's called this general solution, is there anything that these numbers have in common that you can get from one to the next? If you look at it. Well, yeah. They'll have the same denominator because they have the same reference angle. So as you start thinking about it, to get from, if I start here to get to here, it's not the same amount as I get all the way back to here, then, is it? But from first quadrant to third quadrant. Between those two, what are you doing? You're just adding pi. From second quadrant to the fourth quadrant, you're just adding pi. So what's that? No, because if you're adding pi over 2, it means you're going 90 degrees. Okay. So in this case, you're looking to see, you're trying to make the answer as, I don't want to use the word general, but you want to try to make the answer as basic as possible. So it would be pi over 6 plus pi n and 5 pi over 6 plus pi n.
So basically, we don't need to do that extra work.
What do you mean?
Like, we don't need to find the 7 pi over 6 and the 11 pi over 6.
You do, but when you write out your answer, it's going to ask you for it in as simplistic terms as possible. This is as basic as we can get.
So technically, that's more simple than that?
Yes. Because that answer is all answers within one revolution. These answers tell me if I spin around 27 times, I'm going to land on one of these two angles. Yes, sir?
I'm confused because I get what the pi n means, but I don't know. It just doesn't make sense.
To go from 1/6 to 7/6, how much did you add?
Well, you're adding ones.
Right. That's the kick. How is there any, what you're looking at when you write out your solutions within one revolution, you check to see between those values, is there some commonality? The commonality that we found was that between pi over 6 and 7 pi over 6 is a pi, is 1 pi. So no matter what, if I add 1 pi to this, I'd end up here. If I add 1 pi to this, I'd end up here, and back and forth. So no matter what, these two would just be opposite each other each time. Same deal going the other way. You're just trying to figure out the quickest, easiest way to write it out, and that's what the general means.
How come you don't put 7 pi over 6 plus pi over 5?
If I wrote this, it's still correct, but I'm trying to say that this was just happened to be the first one that I saw. You don't have to list that one out, because if I add 1 pi to this, I end up at 7 pi over 6. You're writing, this is more basic than that. This would be all answers within one revolution for the pi over 6, 5 pi over 6, 7 pi over 6. This means if I spin around 27 times, I know I'm going to land on one of these angles. That's all it is. These are giving you all of your coterminal angles that you could find, if that makes more sense.
So if it's plus or minus, there's a two general statements?
Sometimes. And then that's the idea. It's a matter of, you might actually only get, you might have 4 of them, or you might even have 1.
So there's not a set number of general solutions?
Nope. Yeah, if you think about it, if you had plus or minus, if your answer was a tangent value and it wound up being at 45 degrees, doesn't that happen? It happens all 4 quadrants. So that's 90 degrees, 90 degrees, 90 degrees, 90 degrees. That could have been pi over 4 plus pi over 2n. So you could get something like that and get really, really basic. Yes, ma'am?
Shouldn't you, if you're actually writing out the answer, shouldn't you do pi over 6 comma pi over 6 plus pi n to show and then 5 pi over 6 plus 5 pi over 6 comma 5 pi over 6 plus pi n.
Oh, by stating that that's the first angle?
Yeah. Because then
I guess that makes sense, but that's never been written like that. I've never seen it written like that, but I totally understand what you're getting at there. That makes total sense. You don't need to, though.
Okay.
Okay, but I see what you're getting at. Right? You're saying that, hey, I'm going to start here, and then this is the oscillation. That's a great way of writing it, but I've never seen it. Hey, how are you? I've never seen that. What were you saying? Oh. Oh. Oh, hey, congratulations. I saw you guys won conference.
Yeah.
That's awesome. Were you able to throw?
Yeah, I got 15.
Nice.
That's decent. The first one.
I had my first tournament yesterday too.
You were back to playing again too?
Yeah.
Jeez. All right, let's try another one. General solution. I saw the country club was open.
It is?
People were playing yesterday. We drove by.
Oh, people might be playing. I don't know if the course is actually open.
I wanted to get out and play. I just don't have time. So we'll try to we'll do the same idea here. But in this instance, do I need to do the U substitution? What am I going to do? Yeah, I'm going to go right for GCFs here, okay? So we have 2 sine to the fourth x minus sine squared x is 0. Which means the first thing I'm going to do is factor out a sine squared. Take out the GCF. And now I can set 2 separate things equal to 0. Okay with that? So, sine squared x is 0, and 2 sine squared x minus 1 is 0.
Oh.
That's a 0, not a no. Sorry. It's just not funny. Anyway, square root it. What's the square root of 0? 0. Do I have to worry about plus minus when I take the square root of 0? No. So this is going to ask you what angle has a sine value of 0.
I thought that said 25 inches squared.
Come on, it's almost April. You should know my chicken scratch by now. Sine being 0, that's the y coordinate. Where is the y coordinate 0 on the unit circle? 0 and pi. You okay with that?
I didn't say that when you said it. I was
So I'm going to be at 0 and pi. And I'll come back and list out general stuff here in a second. We'll solve each of these first and then do general. The next one, we have to add 1, divide by 2, and take the square root. I'm not going to rationalize this again like we did the other day. Bless you. I'm going to write this as 1 over the square root of 2. Is that all right? This is quicker to see where you're going. That's all. So x is going to equal what angle has a sine value of plus or minus 1 over root 2, which means it has to be a 45-degree angle, correct? So if I'm going to be at a 45-degree angle, that's going to be a pi over 4. How many of those are there? There's 4 of them. So this is going to be all 4 quadrants of pi over 4. So we have pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. That's how we get to all 4 spots. You okay with that? So now let's talk about how do we write this in terms of a general solution. Well, if I go back to the first one, starting at 0, getting to pi, getting back from pi to 0, from 0 to pi and pi to 0 is the same distance. Everybody okay with that? It's just pi. So what I would write is, yes ma'am?
To figure out like when, like in what other quadrant it's going to be positive, do you just do like the all students take calculus?
Yeah, you can do it that way, or just remember that it's plus, minus, minus, and plus, minus.
So you think of it,
Just as ordered pairs.
so like if it, so then you think of it like cosine sine?
Yeah, because that's
But
what it is.
What if it's tangent?
That's sine divided by cosine. Positive divided by positive is positive. Positive divided by negative is negative. Negative divided by negative is,
Wait, that's sine divided by cosine?
yeah, y over x. So this one, my general solution for the first one would be 0 plus pi n. I know it's weird to have 0 as being your answer, but that's your starting point. And then every time you add pi to 0, you wind up at the right angle. Well, as the correct angle, not the 90-degree angle. That's why I always say it's sine SIGN. It's just, I guess I get the Murphy, just keep going. pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. What's happening between each one of those angles? How much are we going up?
Pi.
We're going up half, right? We're going half a pi each time. We're going up 2/4 each time. So the most basic way to write this out would be pi over 4 plus pi over 2 n. That's the idea where sometimes if you get all 4 quadrants of 45 degrees, the difference between each one of them is 90 degrees. If you have all 4 quadrants of 30-degree angles, it's not going to work. And then you'd have your plus pi ends with 2 of them. But that's how it's basically you can get.
Wait, how do you know that it goes in all 4 quadrants?
I had that plus minus. Anytime you see a plus minus, when you take a square root, you're going to hit all 4 quadrants.
Okay.
Because when you take the square root, you're going to have to do plus minus.
And then you're gonna have to do like where the other spot that it is like.
And,
positive.
and you're just using reference angles.
Okay.
That's all.
Wouldn't it be pi over? Oh wait, no, just kidding. That's happening.
This is the one that I wanted to show you because I'm going to add to you guys. We haven't quite gotten to this section yet, but I think that we'll be okay if we have to throw in one property for solving these. In this case here, when you have a cosine and a sine, we need to be able to rewrite the trig functions as one trig function. So we have to come up with a way to do so. Yes, sir?
Can't you just divide and turn it into
Not quite, because you can't just divide out because there's this, okay? But what I want to show you guys is back to the unit circle, back to the triangle. That's your y value, that's your x value, and this was your radius, right? What's the Pythagorean theorem? A squared plus b squared equals c squared, okay? What was the radius always in the unit circle? It was 1, right? What's your y value on the unit circle? What's the y value stand for? Sine. So x is the cosine. So if you think about this, if you take your cosine and you take the sine, isn't that cosine squared x plus sine squared x? Doesn't that have to equal 1? Because of the Pythagorean theorem? Well, it does.
how do you get 1 then?
What's the radius?
Yeah,
What's the radius? What's the radius of the unit circle? Always.
I don't get how you get
What's your ordered pairs on the quadrantals?
0, 1, or 1, 0, 1.
Yeah. So no matter what, your radius is always 1 on the unit circle. It always simplifies it out to equal 1. No matter what. Because your sine and cosine values never are larger than 1 and they're never smaller than negative 1. So the radius is always 1 as you go all the way around. So as you start to think about the plate, let's pick up a picture of it here. Oops. As you're looking at the unit circle, no matter what, it starts at 1, stays at 1. The radius never changes on a circle. So if your radius is always equal to 1, as you go all the way around, that's why this stuff works. Which means then we can use what's called a trigonometric identity. Yes, that's a thing. You're gonna love them. It's called algebraic proof. It is the most hated section in this entire trig unit. And we'll do it after trig break, so but one thing we'll use today is this. cosine squared plus sine squared will always equal 1, which means you can rewrite sines and cosines in terms of one another. By manipulating this, I can say that sine squared is equal to 1 minus cosine squared. Or cosine squared is equal to 1 minus sine squared.
So basically, if you have a sine, you can find a cosine.
Yeah.
Or vice versa.
Yeah. So when I see a trig equation, back to where we were starting with this, when I see a trig equation that has both sine and cosine in them that are not squared, I need to create them. I have to create something. So, what's that? Yeah. So if you square one side of an equation, what do you have to do to the other side? Square it. So you wind up having to set up something like this. We're going to square both sides. On the left-hand side, you have to FOIL it out. It's 1 minus cosine. So you'd have 1 minus cosine times 1 minus cosine and FOIL it. On the right side, it's just root 3 times the sine. So you just use the power of excellence to just square it. So you get 3 sine squared. Is that okay with that? You seem worried. You all right? That wasn't very... All right. FOIL this out. We're going to get 1 minus 2 cosine x plus a cosine squared x. Notice I didn't kill any pugs. On the other side, you get 3 sine squared x. Now I'm going to use substitution because cosine squared plus sine squared is always going to equal 1. I have a bad habit when we do identity stuff that I tend to leave off the x. The x is always there. There's always some theta. The reason that identities work is because that value of x is going to be the same for both angles. So if you don't see me right next, just it's really there. It's not that big of a deal. It just kind of gets in the way. So I can say that sine squared of x is going to equal 1 minus the cosine squared, just by moving this over. So I can use substitution because I have more cosines than I do sines. I'm rewriting sine squared in terms of cosines. All right. Distribute. And now you're back to picking on the little guy and setting one side equal to 0. Okay. Subtract the 3, add the 3 squared, 3 cosine squared. And I'm going to get, what would that be, negative 2 minus 2 cosines of x plus 4 cosine squared x. I'm going to rewrite that in a descending order because it looks a little bit nicer then. And what's the first rule of factoring? What do they have? 2. Factor out the 2. Since I'm solving it for 0, does that 2 have any bearing on the problem whatsoever now? Nope. Factor out 2, you're left with 2 cosine squared minus a cosine minus 1. What times what's negative 2? You add together to get negative 1.
Wait, be sure if you add the 2 and then subtract and then have one, oh, well, same thing.
What's that? -2 and 1, good. Could I do that, remember, remember a couple minutes ago I did that whole U substitution thing here? Could I do that if I wanted to? I can, but since it's only just a square term and an x term, it's generally you could probably pick up on it. So you're gonna wind up with 2 cosine squared x minus 2 cosine x plus 1 cosine x minus 1. And you're gonna factor by grouping. Oops, sorry. Take out a 1. And you're left with this.
Wait, where did you get the extra, plus 1 cosine x?
This one, what I did here was, so this became 2. Became that. I just factored, multiplied my tails to add in the middle. And then you have the answers to go from there. What angle has a cosine of -1/2? What angle has a cosine of 1? And those would be your solution. Sorry to bore you.
Don't,
I'm just moving up. I'm not going into one. I'm just moving up.
I don't know, I still don't have
I just factored this. I have to factor that. What times
any.
what's?
It looks like you just have the same, but then you just add it because.
It was this. What times what's -2? You add together to get -1. Bless you. -2 and a +1, and then I just factored by grouping. So you have cosine. Where's cosine -1/2? Where's cosine 1? All right. Cosine -1/2 would be what, second quadrant at is that 60? So the yeah 2 pi over 3. Something my head was hurting. So you're at 2 pi over 3. It's also negative in the third quadrant. That would be at 4 pi over 3. Where it's equal to 1 is at 0. Well, that's -1. Wait. Yeah, it's at 0. One, 0, 0, 1, -1, yeah, so that's 0. Now, in this case, if you visualize what you're at here, if this was solved for 1 revolution, those would be your 3 answers. If it was a general solution, 2 pi over 3, 4 pi over 3. To get from here to here is not the same distance as 4 pi over 3 back over. So there's nothing that I can add to each of those, that 2 pi over 3 and 4 pi over 3, to get me to oscillate between the two. You understand what I'm saying by oscillating, by getting back to the same spot? So if I had to do a general solution, this would be plus 2 pi n, because it takes me that long to get around, plus 2 pi n here. And same thing with the 0, just be plus 2 pi n. So depending on how the question's worded, it might say solve within a revolution or solve within a general solution. Okay. So yes, trig equations can get a little messy. Smidge.
So wait, so how did you know that it was, you could put it in the third quadrant here?
Where's cosine negative? Since you're at this was the 60-degree angle, so it's second quadrant and third quadrant, cosine is negative. So this comes over to 2 pi over 3, and this comes down another pi over 3, and that's where we got the 4 pi over 3. Try.
I don't get where you get 2 pi.
How long does it take you to get to start it? If you're at 2 pi over 3, how long does it take you to get back to 2 pi over 3? If you're at 4 pi over 3, how long does it take you to get back to 4 pi over 3?
2 pi.
There you go.
But aren't you getting from one point to the other?
Is that the same distance from that point? When you're doing that, this distance from 2 pi to 4 pi over 3 is different than 4 pi over 3 back. Since those two distances are different, there's no standardized oscillation between the two. Whereas if it was 2 pi over 3 and it was, would that be 5 pi over 3? These two distances are the same coming back and forth each time. Between here and here, and then coming back around, they're different. So you cannot show that there's a standardized oscillation between the two. That's why it's just, how long does it take you to get back? One full revolution, one full revolution, one full revolution, and so on. That's all. General solutions take a little while to get used to. Okay. Let me give you a couple of these to put on there. It's on the next page over. So it's on the next page over 34, 35, 37, 38, can't do 40, do 41, and 42. Do general solution with these. I know the instructions say to use it within one revolution, but I want you to try the general solutions on those guys. You will have to do that sine squared, cosine squared trick on one of them. I don't think the other ones you should be okay on.
You have to use the U thing.
You might.
I don't.
Oh yeah, 42 you have to remember how to set something up. See if you can figure it out. We'll keep practicing this again tomorrow, probably, more than likely. Oh, oscillation.